I'm Vicky Nash. I'm Director of the OII. I'm also Associate Professor and Senior Policy Fellow here. And it's obviously a huge pleasure to welcome you all today to hear my fantastic colleague, Dr. Luc Rocher, who's going to give the talk this afternoon. The title, as you can see, is a really great one. So Decoding Deceptive Algorithms, Risks, Public Accountability and Regulation. And it's going to focus on the sort of inherent brittleness or vulnerabilities, if you like, of algorithms and increasingly data-centric technologies. Dr. Rocher is the Programme Director of our very own DPhil in Social Data Science, which I'm eternally grateful. They are also Junior Research Fellow at Kellogg College, and they organise the Hot Topics in Privacy Enhancing Technology. None of these are very easy on the tongue when I say Luke, workshop, and you also serve as the Area Chair for the 2024 ACM Conference on Fairness, Accountability and Transparency, which is obviously one of the major events in our field. Luc also holds a PhD in engineering from the Université catholique de Louvain, which is a great university. In terms of format, I think the presentation will last, what, 30 to 40 minutes, something like that, and then there'll be time for Q&A after. If you're joining us online, then you can do your questions two ways. So you can pop your questions into the Q&A box and we will read those out for you. If you want to be on camera and on mic, you can stick up your hand using the raise hand function, and ideally I will spot you and you can ask a question that way. Obviously, if you're in the room, just hold on to your questions until the end of the talk and stick up your hand in the usual fashion. For everybody's awareness, just note that the event is being recorded and it will be posted on our website following the event. I think that is everything. There's no planned fire tests, so if the alarm rings, obviously you make your way orderly to the front. Other than that, Luc, thank you so much, and over to you.
Thank you, Vicky.
Thank you.
How does it work? No. Very good. So I have about 40 minutes to talk to you about data and algorithms. It's a very broad topic, and in this lecture, I want to highlight some of the limitations that we rarely hear maybe about the way data and algorithms are being used increasingly. Now I think there is probably a broad consensus in the room and beyond in scientific communities that data and algorithms have taken an unprecedented scale. Data is used everywhere in academic research, in also like a lot of departments, states, organizations are using data for public action, and throughout society in so many countries, data is taking an increasing important role. And algorithms are the one that mediate or sometimes build upon this very large data sets of human traces. At the same time, there's also computer science research and research from other fields that show that algorithms are very brittle. They have vulnerability, they can be exploited, leading to numerous failure and harms and manipulations. I pointed to a few examples here from misuse of COVID contact tracing apps that allowed unprecedented access to data that people thought was actually protected and anonymized or private, to technologies that try to anonymize data sets and were actually found to be not super good, and I will come back to this, to numerous examples of algorithms used by public sector and private companies that were found later often by journalists and researchers to have a lot of opacity and eventually evidence of risk and harm that managed to be surfaced. At the same time, I think there is also numerous false promises, deception, what we'll call snake oil, about data-centric technologies, algorithms, and large data sets about people. Often we hear, for instance, do not worry, we're collecting a lot of data about you, sensitive traces, but your data is anonymous. There's no issue, everything is private, confidential, or at the same time, we're building algorithms, but do not worry, the algorithm is very accurate. There's no issue at all. And in this talk, I want to make a very high level depiction of how computational research can be made to try to build evidence about the limitation of technologies in practice, trying to expose often deception about technologies, increase transparency, bring more accountability against technologies that are often very difficult to study if you don't have years of experience in computational research about them. And also hopefully having make a case that numerous inquiries from legal studies, from public policy, social sciences, even philosophy actually requires this evidence by security, privacy, fairness researchers about the failure of algorithms. And without them, it's quite difficult to talk about the regulation of AI technologies because you don't really understand actually what are the practical limitations. And there's a lot of nuance here that I will show. I will have two separate stories, one about data privacy anonymization, and later on a shorter one about pricing algorithms in online markets. Now, just to backtrack a bit, I think, again, we all probably realize that our digital footprints are now widely used by private companies, organizations, and academics. Often we may give consent to, for instance, our NHS data being used for research. They're widely used for healthcare research to support cancer surveillance, or mobile phone traces can be used to support, for instance, humanitarian aid, understand how people move in reactions to a particular event. At the same time, also sometimes we don't give consent for our data to be used, and our data is still used for numerous research purposes. And the reason why is that our data is used in an anonymized way. The reason is that it allows data to be used very broadly without having to require consent from people, because the data is de-identified, private, anonymized. Now, I'm not a law expert, so there are probably people in the room who know this better than me, but if you look at the definition in the GDPR and in like similar regulation worldwide, the notion of anonymity is not very well defined in technical terms, which is normal. It's defined in a very general legal language. Anonymity is somehow defined in a negative way. If you cannot re-identify someone considering available technologies, new technological developments, then data is probably anonymous. The goal is to often break the link between a person's data and data that will be shared with an analyst. But the way it's being done in practice actually extremely complex. There's a broad range of software techniques, algorithm research that have been proposed. 40 years of literature on what is called de-identification or statistical disclosure control that try to take data that is very sensitive and progressively make it less and less sensitive till the point where it's probably fine. So for instance, if you have data with demographics and some more sensitive fields, you might want to remove every direct identifier such as name. Then you think, oh, is that enough? So you might want to remove things like the date of birth and convert it to the year or decade of birth, etc. Till the point where you have a data set which is fairly more confidential. There are many other techniques. You can add noise here and there. You can try to generalize some fields. You can try to use more advanced techniques such as key anonymity. I will come back to this later. At the same time, there's also numerous examples of data sets that have been anonymized with these algorithms, and then people, journalists, researchers found out that these data sets were not anonymous at all. That includes, for instance, Donald Trump tax records. The New York Times went and looked at the IRS data sets of top earners, which was publicly available, and find an outlier in the data that correspond to Donald Trump. Numerous other examples. There was a high-ranking cleric, I think, in the US, which was tracked from a data set from Grindr, the dating app, that was sold in an anonymized way. And I think journalists were able to track the mobility pattern of that person and match to a single person different between different places of the church. And numerous other examples from healthcare and other fields. Now, research has progressively shown that a lot of these techniques that try to de-identify data are actually not fit for purpose. That includes trying to simply pseudonymize data sets, or I mentioned trying to remove direct identifier, coarsening a bit. Researchers have found colleagues that in numerous high-dimensional data sets, such as mobility patterns, just knowing a few data points about people allows us to actually re-identify them very accurately. Example often given is that 4 data points approximate location, 1 square kilometer, 1 hour, are enough to identify 95% of the people in a data set of 1.5 million people. Often people claim that this is like a very old technology, it's fine, we know that this doesn't work. There are more advanced algorithms and software, such as, for instance, k-anonymity, where you take a data set and you progressively try to coarsen it, replacing date of birth with the month, the decade, etc., replacing a postal district by more like a regional district, etc. Until there is enough people that look a bit like you, and it's fine. You're a bit more protected. So for instance, you could be hidden in a crowd of 100 people who all share the same demographics as you, meaning that it's not possible to identify you anyway. Turns out that 2 years ago, there was a researcher, Aloni Cohen in the US, who managed to find out pretty big failures in this algorithm that try to take sensitive data and make it k-anonymous, make sure that there are always k rows that look like you in a data set. What he found is actually a lot of the software that try to, an algorithm that try to make data anonymized, actually try to make it by optimizing two objectives. One is trying to protect privacy, and the other is keep as much information as possible. So for instance, if you have a data set like this, with simply 2 columns, binary, each row is 1 person, and you want to make sure that each row actually is in a group of 2 rows that share the same information. You can do it by coarsening some fields. Here, the same 2 rows look the same because every value has been redacted, and here, the same here. Or you could do it by simply removing 2 cells here, so that this cells and this cell look the same, and this cells and this row and this row look the same. Now, a lot of these algorithms that try to anonymize it will pick this version, because this version has more information than that one. And what Aloni Cohen did is that found a way to reverse engineer by figuring out that a particular data set has been generated. You can reconstruct value of cells and progressively reconstruct the original data sets. What is interesting here is that the method for k-anonymity, I think, is now 2 decades old. And for 2 decades, people use this algorithm and software. We find findings this like big vulnerability and still continue to use it. There's another issue, which is that often, even if you find re-identification attacks in this de-identification software and algorithms, there's always a last line of defense that I think proponents of this software often try to use, which is uncertainty. I will give you an example. In 1997, Latanya Sweeney, which was a PhD student, I believe at MIT, now a professor at Harvard, found out that there was a medical data set in Massachusetts, in Boston, with medical data about a lot of public servants in all of Massachusetts, with a lot of demographic, ethnicity, birth dates, postal codes, gender. And there was actually another data set publicly available for, I think, $20, containing all the voter registration of about 55% of all the population. And she simply matched the 2 data sets, looked at the governor, William Weld. There were 6 people with the same birth date, 3 were men, and only 1 was in these postal districts. So matching the 2, she was able to figure out all the medical data about the governor and mailed to him all the information she found, and the dataset was taken off. Which is a great example of issues, basic issues in terms of privacy. But unfortunately, a lot of people actually claim that there is a fatal flaw here. The issue is that Latanya Sweeney wasn't very sure that the record she found that was unique and matched here was the one that believed to the governor. Could have been another person not in the voter list that had the same postal district, date of birth, and gender. And often, if you point out that the re-identification attack that is possible to figure out, even in very complex AI-based anonymization software, that there is a flaw, turns out that you're always never sure you found the right person. It could always be someone else who share the same information. And there's really like two camps here, and a lot of people would try to claim that re-identification is actually not possible because you're never sure you found the right person or not. And it's where we come to my research, where for many years I tried to figure this out. What if we could actually quantify this uncertainty and try to figure out how likely we are to have found the right record when we try to re-identify someone? The way we did it was actually building a small statistical model, and I won't go much into the details, but training statistical models on a few hundred or thousands of records that is similar to the data used to identify someone, learn how the data is distributed, and then extrapolate to the overall population to try to count how many people have the same combination of attributes as you, which allow us to say for the overall population, how many people could be identified, but also for a given person, what is their own risk. To give an example, again, we replicated this example of the governor, William Weld in Massachusetts, and found out that, yeah, with his postal district, date of birth, gender, there was about 58% chance of being unique and of having found the right match. If there had been a tiny bit more information, such as the fact he had 5 children at the time, it would have gone from 58 to 99.97%. And the key takeaway here is that we can now quantify actually what is the likelihood for someone to be unique and therefore always re-identified. And probably with just a few extra attributes, it's often fine to re-identify someone quite accurately. We built a website, the Observatory of Anonymity on OOA.org, where you can go and you can actually play with the model and try to understand how much data is enough to identify you. And of course, the more data, the more likely to identify. There's a small quiz that you can fill, and progressively you realize that actually with just a few attributes known about you, someone is going to be able to accurately identify you if they find you in anonymized data. Now, okay, we understand that very simple algorithms that try to de-identify data probably don't work very well, or at least there is a lot of fundamental issues. But maybe there are better anonymization algorithms out there. What about techniques that try to stop releasing data? So you take data, you anonymize it, and you release forever. To techniques that provide maybe better guarantees. There's a range of privacy enhancing technologies being designed, techniques where you send queries and get aggregated results and return synthetic data generation and a whole range of other techniques. Let's pick one, for instance, the first one. A few years ago, people from researchers from the Max Planck Institute in Germany presented a new database system called DPhil. It's a database with an algorithm that tries to enter all your queries about underlying data with a rich syntax. So you SQL syntax for those we know. So you can send many queries. How many people have these attributes? Can you count? Build me an histogram, etc. As many queries as you want, and it will answer with a tiny amount of noise to protect privacy. It was guaranteed by the CNIL, the French DPO, to be GDPR level anonymous. Now it's quite difficult to build this sort of system well. One reason, for instance, is that you want to make sure that, let's say, the University of Oxford release data about all the earnings of all the staff members. And my colleague thinks I'm earning too much for what I do. So they go and they ask, how many people named Luc have a salary higher than £50,000? And if the database answers one person, then they know that I have a salary that is probably too high. So you want to make sure that these sort of queries are not possible. So you can look, there's only one person, it's too slow, the query size is too small, so let's forget this. But then people found out new ways to figure out how someone can be identified. You can ask 2 queries. How many people in Oxford have a high salary and how many people not named Luc have a high salary? And if you deduct both, which actually match a lot of people, wouldn't be would be approved by the database, you can still re-identify me and understand my protected attributes, say the fact that I have a high or low income. And numerous attacks have been proposed. And DPhil, the database, try to make sure that none of them are actually possible using a combination of quite fancy techniques, small heuristics. So for instance, if you want to ask how many people at Oxford have a high salary, it will answer, let's say there are 534 people, it will not answer 534. It will add a tiny bit of noise and say 535 plus 3. So you're not sure exactly. So when you start to build different queries to try to do intersection, try to figure that information, there's more and more noise that carries on. And the way it does it is even more complex. There's noise added based on different parts of the query, depending on the data distribution. And the way it's done is that you're not supposed to figure out any information using all these standard attacks. For instance, building differences of query to figure out information about people. Now the issue is that even all these protections are not enough. What we looked at it for about 6 months when I was a postdoc at Imperial, and eventually we found out there was one clear vulnerability that we could design actually specific queries taking into account the noise that was added to protect, for instance, protected attributes about people. We found a simple way to generate a number of queries that would fluctuate or not, depending on the values of the attributes. It's fairly technical, but you can go read the research if you're interested. And basically, we could find that using 32 queries about someone, we could predict a value of a sensitive attribute with 91% accuracy, enough to have like a certain level of confidence about someone, say, protected attributes, which was the first real world example of an attack where you use a noise that has been added actually to exploit and find vulnerabilities in the data. And they acknowledged the attack. Other researchers came and found other vulnerabilities in the system. I think the moral here is that protecting this sort of databases with a high utility while trying to achieve a very high also amount of privacy guarantees is quite hard. So what is next? We heard about probably differential privacy many times over the years. At least I did. It's a fairly formal definition, mathematical, of how an algorithm tries to preserve privacy. An algorithm takes as input a data set and output an answer to the query, to any potential query, and try to do it in a way that you can't predict any information about people in the original data sets. Actually, even if someone was not in the data set or was, you would not be able to figure out this. It's a fairly technical definition. It's quite hard to implement it, but people have started to use it. Google, Apple, Uber, even the US Census tries to do it. Often a lot of controversies around it. Social scientists are not super happy with the use of differential privacy in the US Census. Researchers believe that Apple didn't implement it well enough, but still it's progressively used in numerous applications. It's been, for instance, used by Google in 2019 when trying to release mobility data about 300 million people. If you opted in location history to have your location history with Google, you've been included in a data set shared with numerous researchers who did research about mobility of people worldwide. And they added differential privacy to it. They considered trip flow information, basically origin destination matrices, how many people go from London to Oxford in a particular week, adding a tiny bit of noise here and there to release information with this level of privacy, which they call very strong. There's a lot of mathematical discussion assumptions. There is a privacy parameter epsilon that you can vary, and they set low enough that in theory it's supposed to provide very strong guarantees. And we looked at it, we looked at the research, the appendices and the Nature papers where they were defining the guarantees, and it didn't really make sense. So we contacted Nature, it went to Google and back to us for a year until now there's a response that somehow, I think from their side and from our side, agrees that the way they defined it was not enough, and actually there was not much meaningful privacy guarantees in the way they implemented it. Basically, they made one core assumption, which is that one user contributes only one trip in the data set. And actually, they had weekly trips from people, actually many different trips per week, potentially across multiple years. For instance, that is 39 trips recorded by Google. I think at the time, the week they recorded, 2016, meaning that they assume an attacker would have no chance, according to very strong assumption, theoretical guarantees of identifying me. And in the scenario they consider, actually would go from close to 50% random baseline to 95% accuracy of identifying if I was in the data set. And they acknowledge error. It was too late for it to be changed, and potentially fixing this core assumption that they made would actually require so much change to the data that it would not be actually of any use for the geographer and social scientists who used it. I think just a small caveat here is that they considered a very strong theoretical model of privacy. It considered a very strong attacker. So for instance, even if you know information about n-1 people in one very large data set of n people, say 1 million, you should not be able to infer anything about the remaining person. But at the same time, in this very strong theoretical model that they consider, the guarantees that they try to make were actually voided. And then there's the discussion about the actual privacy you get when the data is released, of course. So differential privacy is very interesting, can be done well, but also it's quite difficult to implement perfectly. So what is next? Let's take a last example, synthetic data. We often hear about synthetic data generation is a new thing. You take raw sensitive data and you have an algorithm that takes it, goes through a sieve and generates new records that are all different. They're all artificial. They share no information about the original person. It's used by the NHS, by IOM, and numerous organizations. The goal is to try to actually pivot away from technologies that are either too hard to use or not secure enough. But at the same time, a number of people have started to argue that it might not actually be that secure. So for instance, if you find an outlier that is a bit too unique, there might be a record that actually clustered a bit and look alike that person you're looking for, and you might figure information about them. Some people claim that no, it's fine. Synthetic data is very safe. We looked at it last year with colleagues at UCL and a former postdoc of mine, and we tested a range of algorithms to try to generate synthetic data sets and propose a new attack that try to predict, again, a sensitive attribute about a potential target victim from less sensitive attributes that might be known. And the conclusion here, again, is very nuanced. There's a lot of technicality, but is that we couldn't find any single algorithm that could systematically either provide a very high statistical utility in the data it generates, while also having very strong privacy protection. Either you have one, either you have the other one. We found that any potential user in the dataset could be vulnerable, of course. This figure, I'm not sure if it's easy to comprehend, but we try to plot two things. One is a relative error in statistics that you can extract from a potential data set. And here is the accuracy of an attacker to predict a sensitive attribute about someone, a binary attribute. And we found that, well, either you try to make sure an attacker could not reveal any information about potential individuals in the data, but then you end up with relative error of 40%, 60, 80, 100%, which for social scientists it's a lot. You cannot do much with such error rates. Otherwise, you try to have very low rates, less than 20 or 10% relative error. So if you assume that the population in Oxford is 100,000 people, you might end up with 110,000 people. Maybe it's accurate enough, but then you end up with very high accuracy of re-identification. And you have a fairly, not very good trade-off when you look at the guarantees you try to have in terms of privacy and the utility for social scientists, for instance. So the conclusion here, I think it's maybe I'm taking maybe a broad definition of the word deception, but still there's numerous actors in the field that try to claim that algorithms have now been built to take sensitive data and release it with many highly accurate statistics from data while providing very robust privacy guarantees. And on the other hand, there are computer scientists, computational researchers who try to claim that actually doing this is hard and often impossible. You cannot both release a lot of information that will be of use for public action, healthcare researchers, social scientists, while protecting the privacy in a meaningful way. There are many, I think, rigorous privacy solutions from differential privacy that I mentioned. If used well, they can release limited amounts of information with good privacy guarantees. But none of them are a silver bullet. And it's quite difficult for each new method being proposed to research them, understand what are the issues, the risks, etc. I will move to a completely different example now. I will talk about algorithms and markets to try to make this claim again, but for very different categories of algorithms. Move also the cursor. So if I'm guessing a lot of you have bought books maybe in person in a bookshop and online, and there's a big difference. You go in a bookshop, you shop, you look around, you pick a book, you go to the till, and you buy the book, and then it's in your pocket and you go home. If you go online, it's actually an ecosystem of hundreds of different actors who look at you when you click on different part of a website to try to analyze what you're going to buy, ending up with, for instance, when you try to buy a book online, you put it in a shopping cart, and then you realize the next day that it went up by 13 cents. And you're not super happy, you wait one more day. It goes down by 22 cents. And the reason why is that there are all these actors that try to optimize the price of all the items in every online markets now. The way they do it, of course, is that by looking at numerous different signals and then optimizing over time how to move the price in one direction or another. If you look, for instance, at the book Bread by Paul Hollywood, and you want to buy it online, you realize that if you plot it over, say, 8 years, it kept moving up and down a lot. For instance, here, during a period of a few months, it goes down and down and down and down, and then it goes up, and there are like these cycles of prices. And the reason why it's not that there's one person who like tweaks the algorithm and then decide to go down by 1 cent every day. It's that there are numerous algorithms that try to compete. One will go down and the other will go down, etc., until the price is too low and they go up. They fight against each other. It's very difficult to understand, but there was a study in 2016 where they tried to estimate how many algorithms are of use online. They found that about 1/3 of sellers on Amazon were using automated algorithmic pricing. Now, algorithmic pricing is fairly complex. You have a software and algorithm that try to optimize the price of a good or service, taking into account numerous different signals. It could be the price set by other competitors, consumer demand, availability of stocks. And there are many actors that try to develop these algorithms in very different ways. Sometimes it's a bit silly and they fail, and it's quite easy to figure out why. We keep hearing of these examples, the making of a fly, where I think a postdoc in biology wanted really to buy the book, The Making of Fly. So they go, it was years ago, because Amazon looks a bit different now. They look at the price of the book and they figured out that it's now $1 million. It's a bit too much. You don't really have the research allowance for this. And the next day is 1.7, and it went up and up, 1 million, 1 billion, 2 billion. And eventually there were actually two bookshops trying to sell the book on Amazon. And this postdoc took his laptop and plotted actually the prices and figured out there was two strategies. One had the book, so was underselling by 0.2%, because they had the book, so they wanted to get the sale. And the other didn't have the book, but was expecting to buy from the other seller if they got the sale. So they were putting a premium of 27%. And if you look at this, well, and if you do it every day, then it will go up and up and up, raising prices at the expense of consumers. But this is completely lawful. It's fine to look at the prices set by other vendors and try to optimize your prices. It's a fairly good practice according to economics regulators and a number of organizations. What is unlawful is for humans, people, to sit in a dark room, smoke cigars, and decide that the price of the book will be 10% higher for everyone for a year. It's fairly difficult to figure out. You need whistleblowers to release information about this, secret regular meetings that are done to try to set prices and gain unfair market advantage. But when it comes to algorithm, it's not really the same picture. They don't sit in a basement and smoke cigars and decide to set the prices. They observe all the prices. They're fairly legitimate tools, some argue, that could be used to make markets better for everyone and finally fix them. And a number of researchers are now wondering whether algorithms could learn on their own different collusive strategies, and they're fairly limited academic evidence. A number of economic researchers believe using simulations with a specific type of algorithm, Q-learning agents, that pricing algorithm could learn to increase profitability. They could all converge to strategies that are supra-competitive, meaning that they start from a level where prices are fairly competitive, and progressively the price go up to a level where it's not good for us when we want to go online and buy a book. They could tacitly learn to consistently charge supra-competitive prices with even punishment mechanism. But if you look at all this research is done often with fairly strong assumptions. It requires that all agents use the same exact algorithm, trained with the same hypothesis, assumptions, methods, weight, and the algorithm are fixed after training, leading to other people to believe that actually there's maybe no risk of algorithm learning to collude in real world markets. As I said, I think this assumption might not really happen in practice. Competitors are all using different algorithms online. What could be possible actually is for algorithms to have vulnerabilities that could be exploited. Something that has been shown in many different fields. Just adding a few different words at the end of an email could make sure that your spam email is actually labeled as non-spam. You can put a tiny sticker on a stop sign, and then the Tesla car doesn't see it and crash. There's numerous examples of algorithms that actually are not very robust and are brittle when you try to manipulate them a tiny bit, which is what we tried to study 2 years ago, looking, again, taking the fairly standard setting of economists who study these markets. You have multiple agents here, for instance, 2, but could be more, who observe market prices. They have a strategy that they use to update the prices, then they observe again, and they update the prices, etc. Ad vitam aeternam. So they set prices. There's a demand function that tries to simulate the demand of a market, that simulates actual consumers that try to set prices. And then agents receive profits, which they use to try to optimize the function and set a good price. And what we try to figure out is simply, can one adversary learn the pricing strategy of other agents and then use it to try to nudge other agents towards prices and perhaps that actually might maximize its own profits, or potentially even raise prices for both agents. So we try to implement this just to show you how it looks like. You start from a fairly low Nash equilibrium, and then you have a learning phase where you try to figure out all the potential prices of another agent till you end up with a good understanding of the other agent. And you can have, for instance, very high profits, while the other agent has very low profits. And we try to do it for many different algorithms using the literature, found out that it was possible fairly consistently. The way we did it is that we learn a graph, a network of all the potential price combinations of all the agents in the market. So for every potential combination of prices, say you price your book at $10 and I price it at $9, we looked at what you would do the next step and what I would do. And then we try all the potential strategies till we understand the entirety of decisions made by the other agents in the market. And we have a small exploration strategy where you try to find the path that leads you to an area you haven't explored till you explore the whole set of combinations. Once we map the entirety of the network, all the potential combination of prices, how other agents would update their prices, we actually have a fairly simple algorithm, Karp's algorithm from 1978, that what it does is that tells us what is the area of this graph where we're gonna have a sequence of prices that maximizes our own individual profits, while, for instance, maybe minimizing the profits of the other agents or maximizing both the combination of our prices and the prices of the other agents. To give you a fairly simple examples, let's say we have hotel rooms in Oxford, which are set around 50 euros or 50 pounds. Now there are 2 different algorithms that are used in an hotel booking website. They all set prices for hotel rooms in Oxford at 50 pounds. They get 50 people in each hotel, and they're quite happy. If you look at the marginal prices, the room costs them 50 pounds. They sell it at 50 pounds. They don't make any profit. What we're going to do is that we're going to explore the prices over a period of a couple of days till we figured out the strategy of the other agent. And then we're going to figure out that we can actually find out a strategy that raises prices for the other agent while keeping our prices a tiny bit lower, meaning that it's going to be fairly more expensive, less people are going to buy a hotel room, but still more people are going to come to us. We're going to make a lot more profits. They're going to make actually a tiny bit more profits. Now they might realize that they're making a lot less profits and sales than us. And they might decide to change and revise their strategy. So what we found out that we can also try to optimize to maximize our own profit while actually keeping the profits of the other competitors high, leading to same number of rooms being sold and same profits for both agents. Of course, at a much higher rate than before still. So everyone is making more profits and every consumer is paying a lot more than before. The conclusion here, I think, is that I think there is a fairly standard opinion that pricing algorithms are fairly lawful. It's quite hard to make them deviate. Tacit collusion has been shown by economists, but it's fairly far-stretched. At the same time, actually, we find that an adversary can learn to understand the strategies of other agents, manipulate them, and end up with very high supra-competitive profits at the expense of consumers. When we did the research, we tried to talk to journalists, and we said, oh, we show that algorithms can be manipulated, it's a risk. And they always say, oh, but is that a risk? Is it really happening in practice? And we're like, well, we don't really know. We think it's a risk. We think it's not the very opaque algorithm. We don't know about the regulation, what will happen. And we're not really interested till I think a few months later when we found out that there is now an FTC case against Amazon, who might have used an algorithm that learns the pricing strategy of other agents to try to figure out the one that can be manipulated and then raise the prices so that the other agents also follow, leading to supra-competitive prices that might have allowed Amazon to make 1.4 billion profits. It's fairly difficult to understand what is happening again, very opaque. I think now there is evidence in theory and hopefully in practice that it is possible. But the regulation and enforcement is very behind. As I mentioned, the use of algorithms can be lawful without coordination, and the fact that there are collusive patterns is not necessarily illegal. What is potentially more illegal is either the fact that a competitor is aware their algorithm has been manipulated and does nothing, or the fact that one agent has a dominant position in the market and can optimize, and this could be considered an abusive move. And just to conclude, I think about these two stories, I think the moral here is that I try to present in very, very orthogonal examples that a number of algorithm data-centric technologies are very brittle. It's quite hard to figure out without months and years of research. But once you do the computational research, you can actually understand that many of them are inherent vulnerabilities. Often they're sold as being very robust, rigorous, and this aesthetic of having algorithms that try to anonymize data or set prices in a very rigorous way hide the fact that they have inherent vulnerabilities. And making research try to expose these cases actually requires years of effort by computer scientists. And increasingly it's harder because we don't have access to what is happening on the ground. We can't really study algorithm in online markets without the evidence. We can't really understand what is happening with data being shared with social scientists from online platforms because we don't really know what source code has been used to anonymize the data. I think what I hope with this presentation was that we can, I think, start to understand that a lot of these technologies are very difficult to study and that we probably need a change of action and practice to make it easier to research their impact in practice. Thank you.
Fantastic. Luc, that's fantastic. Thank you so much. You speak with such incredible sort of clarity and ease on what is really quite a complex topic. So, you know, I think you did a super job, and Mark, thank you for the water again. Right, so I think we've still got quite enough some questions. Who would like to ask in the room whilst I pull up the online ones? Yeah, Jennifer.
Good evening. Thank you for a lot of presentation, and I understand when you discuss why for privacy is important, this the integration of the data and everything. Your game theory example of two observable agents is also very interesting and clear. But my question would be, what will be the future of the research if we further the identified information? So how will you be able to observe behavior of individuals or agents in the market as you presented here, if we don't have that kind of observable information? for decision making, for instance,
Yeah.
marketing or customer hero pricing?
That's a good question. Should I repeat the question for online people? Or?
Yeah, why don't you?
Yeah, so I think I'm gonna answer for the first bits for de-identification and anonymization software. So I was asked, what is the future of these technologies, and how we can hopefully understand how we can better share data if we find out that a number of these technologies are not fit for purpose. I think the first step is understanding that numerous technologies being proposed are not fit for purpose. And of course, it changes with new development. A lot of attacks that I didn't cover use advanced machine learning techniques to try to re-identify information that was not possible 20 years ago. I think at the same time, I think it's important to move beyond the nuance and understand that there is a fair amount of consensus, say in privacy, security communities about some of these technologies. And we can probably, like, I think, agree that some technologies are not fit for purpose and should not be used. It is possible to access data in a fully secure way without anonymization software. You can use a device where you put your biometric information, your finger, and you access a virtual machine connected to a server where you have extremely sensitive information. Someone is recording the screen of what you do. It's very costly. I think we can find better models. I think there are colleagues at the Bennett Institute that try to develop a platform, for instance, called OpenSafely, where you develop code to analyze NHS data, and then the code is being sent to the platform where they look at it, run it on the internal data, and only release statistics that has been looked manually by people. I think there are some trade-offs to find, but at the same time, I think it's important to put first trust maximize trust by people, by citizens, so that we don't end up with people withholding data that would be useful for research. Yeah.
There might have been a couple of questions online.
Yes, there's one here.
Right, there we go. Yeah. So, any comment on the current UK regulatory regime as to whether any of the current or proposed policy proposals seem to help acknowledge or even mitigate these vulnerabilities? My gosh, and for the EU and US as well. Can you just comment on all those policy regimes? Feel free to pick one or none.
Yeah, I might respond a bit, I don't know, aside, because I'm not a law scholar. My understanding is that as a computer scientist by training, it's very difficult to understand like the subtlety of the law, etc. The law is not like determining what is like, I don't know, what is a technology that is not possible to anonymize data, which one like allows very like easy identification and sets fairly high level guidance that then are defined and enforced in practice. And there's a lot of work, for instance, done at the EU level, at the EDPB, to actually define something fairly simple, the word anonymization. What does it mean? Some, I think, mathematicians still believe that we can use equations to define what is anonymity. A lot of other people believe it's a fallacy, it's not possible. It's quite hard to, I think, to answer what's happening. I know that some countries and regulation, I think notably in the UK, try to set the bar a bit lower and try to explain that re-identification, yes, it is possible on paper, but it's not really like that easy to do, and probably like we should let data flow a little bit more. I think hopefully the example that I've shown show that it's a fairly high risk, and especially once you release data that is thought to be anonymous and then it's too late and the data is released and someone re-identify it, then you can't do anything about it, and sensitive data about people is out there. So my opinion is, I think setting quite harsh rules about this technology is probably the better way to do it.
Question here at the front.
Yeah, so yeah, sorry, were you pointing at me?
Yes, I was pointing at you.
Okay, I'm Karen Mansfield. I'm working with Andy Szpilski on an adolescent wellbeing in the Digital Age project. I've experienced this kind of issue in trying to collect, share, and link adolescent mental health data. And at the time, I found it really tricky to explain to people why, like, oh no, I really don't think we should be sharing that information. I really don't think we should be sharing that information. And it's frustrating that I wasn't aware of your research at the time, because probably it would have been helpful. But my question is, to what extent, I mean, is there any idea of how the probability of actually identifying somebody positively changes if some or all of the data is self-reported?
So the question was about self-reported data versus data collected in other way. And do you mean self-reported data being less accurate potentially? So harder to
Yeah, I mean,
identify?
potentially even adolescents not telling the truth because they want to hide their identity. So some information is more objective and other information.
I think usually research is done considering that data is extremely accurate about people. If you have accurate variables about example I gave, demographic, postal district, gender, age, then you can model what is the chance of identification. I think taking into account the fact that people don't withhold some information, try to hide some information could make it easier to share data. But then you try to, it's a gamble. You assume that people withhold some information so that you can release more data, but actually if they release the accurate information, they could be identified. So it's probably better to consider they release the accurate, truthful data.
Yeah, that's also always what it's used.
Yeah, you're right. Particularly things like social media, there are strategies, aren't there, for hiding yourself in quite effectively. So yeah. I have a question behind me here.
Hi, yeah. Thanks so much, Luke. So my name is Molly. I'm a compliance officer at Security Health, which is a mental health research company. And a lot of the examples you give are commingling of publicly accessible data sets. My question is, to what extent can anonymization be enhanced by utilizing virtual private clouds and keeping that data segregated so it can't be commingled so easily?
Thank you. So the question was about considering on the one hand public information versus on the other hand doing these computations on virtual cloud internally. I think a lot of the examples I've give consider that anonymity is needed to protect privacy. It can also be considered as part of a data minimization practice. When you have internal data that will never be released, but you want to make the data more a bit less accurate or minimize the risk so that different people in the same company, for instance, can use the data, and you try to make sure that there's less chance of catastrophic risk. I think I'm less aware of what is a regulation, but I think it does make sense to do it, probably. I mean, I think it depends a bit on outcomes, what you want to do with the data. If it doesn't cost anything in terms of accuracy for effect you want to measure in data, yes, try to minimize the data as much as possible to minimize risk and harms. Yeah.
Any more questions on
one here?
Okay. So another good question online. Is there a push for research to be translated into more appropriate information security standards? And how can we help advocate for this?
I think that's a good question, and I don't have a good answer to this. I mean, I think one issue I see that two issues actually. One is that a lot of this research is very technical, and I think for people who don't have the background in applied machine mathematics, machine learning research, privacy and security, it's quite hard to understand what is actually possible, what assumptions you make when you claim that a identification is possible or not. Which requires a lot of expert knowledge on the one hand, and on the second hand, there are very few translation efforts to try to find what is a consensus in, say, privacy, security about, or fairness research about algorithms, and then make a claim that technology X is safe or not. And computer scientists really like to have nuance. So when you submit to a conference and you say, we found a re-identification attack, you need to show how the technology could be fixed. So there's always a new attack and a new fix, and you're not really sure what is being done in practice. While actually, I think it's possible to have a bit less nuance and have stricter, probably, conclusions. Not sure who would be best fitted to do this.
Can I push you on that question actually just a bit further? So you made the very good point a while ago about the role of trust here, and that one of the sort of key things we want to see if you want to be able to use these big computational data sets is to ensure what we're doing over time is increasing, not decreasing, public trust in providing their information. But also what you've just described to me is a sort of wonderful game of sort of almost like sort of cat and mouse, whereas as a computational social scientist, you're keen to expose flaws so that they can be fixed. But of course, the risk is that in exposing those flaws, obviously it's publicizing reasons to distrust. So yeah, how do you sort of think, how do we manage that balance at the end of the day?
I think the way it's being, I think it's maybe more an ethics question.
Yeah.
I'm not an ethicist, so there's no ethicist in the room to criticize me. I think we had the same exact question. I think when we published my first research showing that we can quantify the risk of identification and an attacker can be sure that we identify the right person. And we had this like very strong journalists from the New York Times were like poked at us and said like, oh, but like you found there's like an issue, like what do you think is like the issue like with releasing this? Are you aware of like, I don't know, anyone who's going to be harmed by releasing this re-identification, etc.? I think on the one hand, it's important to point out that there is a risk that we find out as researchers building a new re-identification attack, which might have been known to people before. It's the same issue in security, private data breaches, zero-day exploits for mobile phones and computers. It's important, I think, to build public awareness for people to understand there were risks already, and now we know them. I think we can do it maybe in a way that is safer by like telling companies, look, we found a vulnerability in your software, you have 90 days to fix it, etc. Sometimes they respond to it, sometimes they send the police. A number of, it's actually not a joke, like a number of, I think, students, researchers got the police like called because they found re-identification in a tram system for tickets, for mobility tickets, and numerous other applications, and some of them went to jail because they found they could re-identify people. Some academics were pushed away from universities because they found like very like strong issues with the way data is being shared by the state. There's I think a lot of issues, personal responsibility, career also considerations, very difficult.
So we need the field as a whole, definitely. Yeah. Got time, a couple more questions, probably. Yes.
Hi. Thanks again for the great talk. To the second part of your talk about online marketplaces, do you think it would be possible with an algorithmic audit to identify whether or not an algorithm has the sort of adversarial pricing behavior that exploits the other agents in the way that you showed? Because it sounds like tacit collusion is unlikely, which seems like good news because that would be hard to know if that's happening. But in the way that you said it could happen, do you think that'd be possible to detect?
I mean, on the one hand, if the FTC is making a case against Amazon that they might have used dominant practice and nudge other algorithm, there was some information that they figured out about this. Might have been whistleblower, etc., but they're gonna have to look into the signals and figure out what is happening. So they will have to do it, I think, soon. I don't think the research is there for a simple reason. I don't think scientifically it's impossible. It's probably quite tough. I would like to do it, figuring out like if an algorithm can be manipulated or not, using like real world algorithms and data. But the issue is that we have access to neither is the pricing algorithm being used, neither the data about these platforms. Maybe new regulation, maybe the Digital Market Act in the EU or other worldwide will help with this, but access to sufficient information about all these platforms and also access to probably the code of all these pricing algorithms being used by all these firms, probably very complex algorithms mixed with human in the loop. It's going to be very tough to do like very strong research showing like this was illegal and this was legal.
Any more questions?
Thank you so much. That was excellent. I guess my questions are slightly more general, but you've raised some fantastic examples, including going to the reporters and not being so interested. It seems like this field is fairly responsive rather than preemptive. You're kind of waiting for data to be misused or some sort of, the several examples you gave. I guess my question is, moving forward, where do you see your research or this research heading? Do you continue to kind of build evidence, or is there a shift that you've learned from this research that you would implement in further computational science studies?
I mean, yes, it is true that like if you go to the press and say, oh, we found yet another re-identification, you will be told like, oh, we know it already, and you will be told also more like pressing cases like data breaches. It's not even anonymized data; it's like complete loss of trust from an organization that like released data that's about millions of people. So I think like sometimes I think maybe like I don't know, we're going after I don't know, low-hanging fruits maybe that or not maybe that relevant. At the same time, I think it's important to consider, say, academic researchers who have no choice but to use anonymized de-identified data for numerous research, and there's not that many alternatives at the moment. Especially if you're not in an elite institution where you can go and like call private companies, call organizations, state organization to request some data. Your only like route is using the data set that have been publicly released. I think one important area of research is building better software toolbox and tools actually to use this data in a privacy preserving way. And I think there are actually good ways to use some limited amount of, to like release some limited amount of information while protecting privacy. I think I mentioned example, you send your code to platforms and you get information, aggregated information in return just for what you need. So you do a study, you prepare all the code and you send it and it is run remotely. It's probably, I think, fairer for a lot of researchers than having a two-way system where some people have the fast track access to very sensitive data and the rest of the world doesn't. But at the same time, like hundreds and thousands of people are still looking at like building slightly better privacy preserving solutions, and sometimes actually lead to completely different technologies. I think one example is contact tracing apps. Is it possible to collect very sensitive information about the mobility of people and the social networks just to release a small information, which is has it been infected or not with COVID-19? And for some use cases, I think it is possible to do meaningful privacy computation, while for some others, releasing like the entirety of a data set, I think there is a consensus that it is not.
Fantastic. We've hit 6 o'clock, so we ought to finish. Yes. But I just really want to thank all of you for coming along today, all those of you online for joining the conversation. But if we can just put our hands together and thank Luc for a superb talk.